Welcome to this hardware and software implementation of the Coursework 3 boundary scan test controller. This is group number 5 with Ole Marius Nordrud, Eivind Tangen and Jan Ali. First part of this presentation, me, Ole Marius, will talk about the hardware part, and in the end Eivind will talk about the software part. So for the hardware, we found out that the easiest way to start this is probably by creating a simple GPU. The code was already there on Canvas, so we used this to get an understanding of the architecture of the GPU and how it is implemented in VHDL. And we used this and added a few extra instructions that were not specific to our coursework, but we just used them for some training, as well as to learn how the ROM unit was working together with the CPU. Yeah. So the first that we actually did for our task, for our coursework, was to add all the opcodes for the instructions inside the ROM. So as you can see here, we have stored all the opcodes for the different instructions inside the ROM. This will be used for the program counter. So when the first instruction is run, the program counter will increment, and we will run the next instructions after. After you added the ROM, we could start with the instruction register and the execution control. So for these instructions, the best way to start is to create an ASMD chart for each instructions, because each of the instructions will have different states. And we started with the instructions A0 and A1, which is the TMS 0 and 1, which is quite simple instructions, but it's a good start. On the right here you can see a small part of our next state logic. We have the all 0 and all 1 states, which is common for all instructions. After each instruction is run, you go to all 0, and in the all 1 you will check the instruction register of what the instruction is currently just going to be run. Yeah. So here we have the test bench for the TMS 0 and 1. The TMS 0 has a task to set the mTMS value to 0. It's already 0 here, so nothing really happens. And it's going to run the mTCK for 1 clock pulse, as it's doing here. After mTMS 0 is run, it goes to all 0, all 1 again, and then it goes to TMS 1. And the mTMS 1 is going to set the mTMS value to 1. And as well as the TMS 0, it's going to do 1 clock pulse of the mTCK clock pulse. So everything working fine here. So this is the test bench of the mTCK instruction. The mTCK has a task to do n number of mTCK clock pulses. So in our case, we defined the number of pulses to be 5 here. We just set the integer value of 5, and we use a counter here to count the number of clock pulses run. So as you can see here, it runs for 1, 2, 3, 4, 5 clock pulses, which is the same number of pulses right here. Yeah, so the further work, we did not manage to add the shift n number of bits into the test vector, or the shift and compare. We did not manage to implement those, unfortunately. We found those were quite difficult to implement, but we did understand the concept at least, but it's something we did not manage to implement here. Yeah, and the handshaking I did not implement in the hardware, but we did manage to implement in the software, which Eivind will talk about next. So thank you for me, and I'll give the word to Eivind.
In regards to the software implementation of the boundary scan test controller, we implemented various instructions used in the tap controller. First, we had to declare the different instruction codes or OP codes to determine which instructions we want to use. This can be seen here, where we simply created an unsigned 8-bit ROM array variable, which works as a read-only memory for finding instructions. To the right here, we can see the comparison with the TDO input to check which OP code we want to test. Then we can set the correct index based on the current iteration in the for loop. The for loop is used to iterate through all the possible instructions in the ROM and simply returns the correct index in which of the ROM addresses we want to use. Now, the way to manage and handle the instructions codes received through the OP TDO pin is to use the operate functions as we described earlier to search for wanted instruction. A function related to the OP code will be run as seen to the right, where here we show a simple representation of the TMS0 and TMS1 instruction, where the TMS pins are driven to 0 and 1 respectively. A tick pulse or to the clock is also given based on the instruction we have. So in this TMS0 example, we have set the TMS pin to 0 and also generate 1 pulse to the clock pin. We do the same here, but instead of sending a 0 to the TMS pin, we drive it high with a 1 and also send the clock pin to a clock pulse. To the left is the main program, which reads an unsigned 8-bit value into the OP variable. This variable is sent through the operation code or operation function as a parameter. This OP code is used to declare which operation or instruction we want to run. This was our implementation of the BST controller. Thanks for your attention.